Skin effect, tendency of AC current to flow more towards the surface than at the center. Means if this is the conductor, outer part of the conductor, current will flow more towards the outer parts of the conductor, that is the surface of the conductor. It means the skin of the conductor than at the center. So it is called skin effect because more current towards the skin. It occurs only in AC current flow. It does not occur in DC current flow. I'll explain why in AC, why not in DC. Because the skin effect depends on frequency. This frequency occurs only in AC, no frequency in DC. So it occurs only in AC current flow. What happens due to skin effect? Due to the skin effect, current is more on skin and very less current inside the conductor. Means current distribution is not uniform because high current on the skin and less current inside the conductor. So if we see overall the current distribution, high current here, low current here, so non-uniform distribution. Current density, nothing but J is equal to I by A. I means current. If current is non-uniform, nothing but current density will also be non-uniform. Max current density at the surface and minimum current density at the center. So what happened to the effective area of current flow? It reduces. Why? Because if you take a conductor with skin effect, current is flowing only here. More current is flowing only here. Inside the conductor, not heavy current is flowing. But if we see, all over the conductor, current is flowing. Here, if we compare these two, the area in which the current flow here is high when compared to the conductor with skin effect. So more current throughout the conductor and less current throughout the conductor. So if we compare these two, area through which the current flows is throughout this area. Here area through which the current flows is only on the skin. So when we compare these two, area through which the current flow here is increased, but with skin effect reduced. So effective area of current flow reduces. What happened to the effective resistance? Increases. Why? If current flow reduces, resistance increases. Resistance is inversely proportional to the area. Area means area through which the current flows. What happens to the skin effect? Skin effect increases with increase in area of cross section. This is nothing but these are the factors on which skin effect depends. The first factor is area of cross section. If we see these two things, this is the conductor with large area of cross section. This is the conductor with small area of cross section. If we see these two, here this is the area with skin effect. This is the area where the current flows. Here this is the area where the current flows. Here this is the area where current is not flowing. This is the area where current is not flowing. When we compare these two, this is the area where heavy current is not flowing inside the conductor. This is the area where heavy current is not flowing. When we compare these two, area of the large conductor is high, where the current is not flowing, compared to small area. So skin effect increased because compare these two. Here the area where the current is not flowing is high when compared to the area, this one, where the current is not flowing. High in high area, here current is not flowing. In low area, current is not flowing. So much loss of current in the large area, large conductor, and small loss of current in the small conductor. So skin effect increased with increase in area of cross section. It also depends on frequency, relative permeability, sigma. I'll explain why. Skin effect is due to the self-flux linkages. Self-flux linkages occurs only in solid conductors. So skin effect occurs only in solid conductors. The current density inside the conductor due to AC current flow. We know that current is flowing only on the skin, not inside the conductor. So we'll see what is the current density at a distance of Z from the surface of the conductor. What is the current density at a distance of Z from the surface of conductor? Why we are calculating this means more current is flowing only on the skin, not at the center. So we want to know how much current is flowing at a distance of Z from the surface of the conductor. See, current density at a distance of Z from the surface. Formula is J of Z equal to J naught into e power minus Z by delta. Z means nothing but the distance at which we want to calculate the current density. J naught is current density at the surface. Here. Current density on the surface of the conductor. We can see here current density at surface. Delta is nothing but skin depth. What is skin depth? Skin depth means nothing but distance from the conductor surface at which the current density reduces 1 by E times or 36.8% of its value at the surface. I will tell you how. So the formula is J of Z equal to J naught into e power minus Z by delta. Skin depth is also a distance from the conductor. So if delta is equal to Z, I will substitute here, or Z is equal to delta. Delta is also skin depth from the surface, right? Nothing but it is also distance from the conductor surface. We will substitute delta here in place of Z. Delta delta cancel, e power minus 1, G naught into e power minus 1. Nothing but 36.8% of J naught. What does it mean? J naught is nothing but current density at the surface. 36.8% of J naught. That means that skin depth delta is nothing but the distance from the surface of the conductor where current density reduces to 36.8% of the current density at the surface. Now, skin depth is a measure of skin effect. So, delta depends on skin depth. How it is depending? I mean, whether it is directly proportional or inversely proportional. See, if delta increases, what happened to the skin effect? Decreases. Why? Here, if delta is increased, what happens to this whole value? Decreases. E power minus Z by delta decreases. See, if we see this, e power minus Z by delta, we can write it as e power delta by Z. So, e power delta by Z. If delta increases, what happened to the current density? J is directly, see, I wrote e power minus Z by delta as e power delta by Z. If delta increases, J also increases. If J is increasing, it means that, J of Z. J of Z also increases. If J of Z is increasing, what does it mean? Current density at a distance of delta also increased. If current density is increasing inside the conductor, inside means at a distance of Z or from the conductor increased. It means that current density is increased inside the conductor. So, skin effect is reduced. So, if delta increases, skin effect reduces. Delta decreases, skin effect increases. Now, we will see. See, we have already discussed here skin effect increases with frequency, relative permeability, conductivity. I will discuss how it is now. Delta is inversely proportional to F mu sigma. So, however, pi is constant. No need to discuss about this. Delta is inversely proportional to frequency rate. So, if frequency increases, delta decreases. If delta decreases, skin effect increases. So nothing but F and skin effect F mu sigma and skin effect are directly proportional to each other. See here. Delta is inversely proportional to skin effect, and delta is also inversely proportional to F mu sigma. If you compare these two, skin effect is directly proportional to pi F mu sigma. So skin effect is directly proportional to F mu sigma. So if these are increasing, skin effect will also increase. I said here that it will not occur in DC current flow. I'll explain why here. See, for DC current flow, no frequency. If F is 0, what is delta? Infinity. If delta is infinity, what is skin effect? 0. So in DC current, F equal to 0, no skin effect. In AC current, there is some frequency, so there exists skin effect. So now we'll see how the skin effect can be reduced by using non-magnetic conductors. By using non-magnetic conductors means only in magnetic conductors flux will exist, and skin effect is due to the cell flux linkages. Where this flux will exist? Only in magnetic conductors flux will exist. So skin effect occurs in magnetic conductors. So it can be reduced by using non-magnetic conductors, and also in stranded conductors, because it occurs only in solid conductors. So instead of taking solid conductors, if you take stranded conductors, skin effect can be reduced. And also by using non-magnetic conductors, skin effect can be reduced. I've already discussed why non-magnetic conductors, because in magnetic conductors only flux will exist, and skin effect is also due to the flux linkages. So by using non-magnetic conductors, skin effect will reduce. Now proximity effect. Proximity effect is, it is also tendency of AC current to flow more either towards or away from other conductor in a multi-conductor system. See, by seeing the sentence we can say that it will not occur in solid conductors, because solid conductors is not, it will have only one conductor. So tendency of AC current to flow more either towards or away from other conductor in a multi-conductor system. Proximity effect in multi-conductor system, same as skin effect, it occurs in AC current flow, do not occur in DC current flow. So due to proximity effect also, current distribution non-uniform, non-same. So if we see all these factors, we can say that proximity effect also a type of skin effect. Means the effects due to proximity effect are the same as the skin effect, like it occurs in AC current flow, do not occurs in DC current flow, current distribution non-uniform, current density non-uniform. I'll explain with an example. See here, current density due to the proximity effect. If you take two conductors of a multi-conductor system, the flux is flowing only one side of a conductor here. If you take second conductor, here also flux is flowing only other side of the conductor. In these two areas, no flux means no current. So current is only towards this end, and here current is only due to this end. This effect is due to the mutual flux. Why mutual flux? Because between two conductors only mutual flux exists. Due to this mutual flux only, current is flowing towards the end of this conductor, and this conductor towards this conductor. See, if we see these two conductors, this current is flowing towards this conductor, this current is flowing towards this conductor. So in a conductor only this part current is flowing, in this part current is not flowing. So overall effective area of current flow is reduced. So effective resistance increases. See, proximity effect also depends on F mu conductivity, as we discussed in skin effect. I have already told this proximity effect is due to the mutual flux linkages. That's why this current is flowing towards other conductor. Here the current is flowing towards other conductor because mutual flux always exists between two different conductors. Okay. Practically, transmission lines are not made up of solid conductors but of stranded conductors. Here, this thing we have to remember, length of each stranded is more than the length of transmission line by 2 to 5%. Why? Why? Because if there are multiple conductors, there will not be any spiraling. See, if I have spiraled, see, if I have spiral like this, see, these are multiple conductors. If I have spiraled multiple conductors, I am bending the wire. If I take one of this wire and make it straight, then the length of this bended wire, a spiraled wire, will be more than the solid conductor. How much it is more? Nearly 2 to 5% more. So hence the effect of spiraling or stranding or the resistance transmission line is to increase by 2 to 5%. How the resistance is increased? We can say this because resistance depends on length. If we see the formula, R is equal to rho L by A. Due to spiraling, length of the conductor is increased. The length of the conductor is increased, resistance is also increased. How much it is increased? 2 to 5%. Hence the effect of spiraling, stranding, the resistance of transmission line to increase its value by 2 to 5%. This one you have to remember, it is more dominant in cables. So very important thing is resistance in AC is more than resistance in DC. Why? Because due to skin effect and proximity effect. Due to skin effect and proximity effect, already we have discussed that RAC is high. It occurs only in AC current flow. Due to this, effective area of current flow reduced, so resistance increased. So resistance in AC is greater than resistance in DC. So resistance is nothing but they have given a formula, IRMS square, power loss. This is equal to power loss in transmission line by IRMS square. IRMS square at a rated frequency. If frequency increase, RAC increased. Why? Because frequency is directly proportional to skin effect and proximity effect. So if these two increases, R increased. If R increases, F also increases. So RAC of a resistance of AC system will be 0.03 to 0.05 ohms per kilometer. And one more important thing is proximity effect. Proximity effect reduced by using non-magnetic conductors. Okay, their skin effect is reduced by non-magnetic conductors and stranded conductors. Here proximity effect is reduced only by using non-magnetic conductors, because proximity effect occurs in stranded conductors. So we cannot use stranded conductors here. We can use only non-magnetic conductors to reduce the effect of proximity.